All right, let's go get started. So let me get the lights and whatnot adjusted. If you could get the sign-in sheet started around. So let's see. So a little bit on housekeeping, just where we're at and where we're headed. So number one, I just returned back homework number one today, and I'm passing out a solution as we speak. I'll go over it here in a second, but by and large, I really don't think that there's really too much to talk about. 1, 2, 3, 4, 5, 6, 7. All right, so there's that. Hold on. Okay. Here's this. Okay. I'll get the rest of you as like after class, just so we can sort of get into material. So real quick, so homework number 2 is assigned. If I know on Friday that I forgot to actually hand out homework number 2, so I've got hard copies here. If you did not get a hard copy of homework 2, but I also emailed it out to everybody, and it's also on Blackboard. So I mean, you've got 3 different ways to get a hold of the assignment. It's due on Monday, so you got plenty of time to work on it. And by and large, we're mostly finished with all the material needed to go through it. So I think you all are pretty good. But does anybody have any questions about it? One thing I will mention, I had a question earlier regarding shear lag factors for the angle. Make sure that you're referring to the right case. For instance, the one we did in class, we used case 2 and case 7. Well, case 7 is specifically for I-shaped sections, for W's, for M's, for HP's, for S's. Angles don't apply, so make sure you're using the right case. Everybody good? Another solution. Wait, oh, no, that's the wrong one. This is the one. All right. All right, here, let me hand these out, and then I'll get everybody else as class ends. Make sure and pass everybody else out because I don't want to be going back and forth. I want to sort of at least get into some material. But I got some remaining solutions and homework 1s up here. So if you're missing anything, let me know. Let me also mention real quick the Michael Fitzwater Engineering Scholarship. Now this is primarily for SAME, I mean, you have to be an SAME member to qualify, but it's due on February 1st, so I know they're looking for applicants, so if you haven't already applied, make sure if you're interested to go ahead and do so. I emailed the application to the officers and told them to distribute it to the remaining members. If you are interested in applying and you're an SAME member, you can email me and I'll just forward it on, but it's due on Wednesday, so you need to sort of move on that. Everybody good? Okay. One other thing I will mention real quick, and I'll mention this near the end of class as well, but I think I mentioned earlier in the semester that I was going to start having visitors coming to class, some professors. Well, my first one comes on Wednesday, so do me a favor and try and be on time. That's the only thing I ask. Other than that, you know, pay no attention to that person in the corner, as they said about the Wizard of Oz. You know how that goes. Please don't. All right. So they're probably just going to sit in the back and sort of just keep quiet and whatnot. It's just, like I said, some university level assessment stuff and what have you. Everybody good? All right. So today what I want to do is I want to finish out that analysis example that we were looking at, and then we finally get to start talking about design. So that we finally get to start doing some design stuff today, and I'm pretty excited. So, but before I get into that, I do want to sort of do a little bit of a recap on what we were doing with our analysis example. And this is probably a good place to start. So for the initial part of our tension member discussion, we were focused really on making sure we knew how to assess 2 things. Net area, which we spent a fair amount of time on, and then shear lag factors, which we sort of took a nosedive into last time, and ultimately I think it was pretty straightforward, but of course, if you've got any questions, just let me know. So when we're talking about tension members, we really looked initially at two limit states. We looked at yielding in the gross section of the member and then fracture in the net section of the member. And as we found out last time, it's not necessarily as clear as you would think in terms of which one governs. I mean, you know, if you take a regular old tensile specimen that you used in civil engineering materials and yank on it, well, yielding obviously occurs before fracture. But we're not cutting our samurai sword through the same section when we look at these. Here we're looking at the gross section, here we're looking at the net section. And when we did our analysis example last time, we found that fracture for that particular member governed because the net section governed. We had ultimately a smaller effective net area that mattered when you compare it to the gross area. So this was ultimately the capacity that governed, which we'll get into the specifics of that here in a little bit. Now net area, I think we're all clear by now. To calculate net area, we take our gross area, we subtract out any area lost due to the presence of bolts, and then we add any stagger factors to account for diagonal failure paths. Everybody okay with that? Now remember, we adjust that net area by a shear lag factor. Arguably the most common one is case 2. So shear lag factors according to case 2 are 1 minus x bar over L, x bar being the connection eccentricity, L being the connection length. Remember, connection length is, you know, outermost bolt to outermost bolt, and then the connection eccentricity is from the back of the connected member out to the centroid. So it's just making sure you're using the manual appropriately and looking up the right values. Now slenderness, we haven't done that yet today, but we're about to do that here in a second. So slenderness, you just ensure that your L over R is less than or equal to 300. Now we're going to add to this later, but actually we'll be adding to it today. But that's just where we're at so far. And then this is the member that we were looking at last time. So we had a W8 by 24 to be used as a tension member. We had 2 lines of bolts in each flange, and then each line had 4 bolts, right? The member's made out of A992 steel. It's 40 foot long. The bolts are 3/4 inches in diameter. You've got all the dimensions necessary to assess the capacity. And we were looking at gross section yielding and net section fracture. So we went through our calcs. Let me go to right here. So these are the calcs that we did last time. Starting off, we have our W8 by 24, so we looked up all the appropriate properties. We haven't used the radius of gyration yet, but let me ask you a question. For the W sections, which is the smaller radius of gyration, Rx or Ry? Ry, I make sure everybody's paying attention. There we go. One of the things that you will find for W shapes that will always be the case. Ry will always be smaller, okay? It's just the way that we notate steel sections. I mean, if you have an I section, I sections by and large are stronger in one direction than they are in the other. And that's what Ry and Rx indicate. Ry being smaller indicates that the I shape is weaker when it's being bent about that weak axis. I'll say this about Rx and Ry. We will become experts at assessing things like slenderness later when we look at columns, when we look at members subjected to compression. Members in compression behave significantly different than members in tension because members in compression like to do this little thing called buckling. So that becomes a whole another can of worms later. For now, we're just looking at basic slenderness calcs, so we'll just go off of our Ry. Okay, so we looked up A992 steel properties, and then we said, okay, let's start computing some values. So if you recall, we calculated ultimately 2 limit state capacities. We calculated this one right here, which was gross section yielding, and we got about 318.6 kips. So that's, if I take this member and yank it, the gross section will yield at a load of about 318.6 kips. Keeping in mind, we've adjusted that with a safety factor. We use our resistance factor of 0.9. Now that's for yielding in the gross section. For the net section, little more work that needs to be done because we have to calculate the net area, which we got 5.68 square inches. Then we got to figure out which shear lag factor governs. So we calculated according to case 2. Remember case 2, we looked up the appropriate Y bar for the equivalent WT. So if it's a W8 by 24, we look up the Y bar for a WT 4 by 12. Remember, you're cutting the depth in half, and then you're cutting the weight in half. So it's a WT 4 by 12. So that comes out to be 0.695 inches. So here's our U2, comes out to 0.923. And then U7's really just following the table and following the spec. That comes out to be 0.9. And then which one do you use? You use the larger according to the notation in case 7. And then finally we get a capacity of 255.6 kips. Is everybody okay with that? Everybody good with that? Okay, now, so if everybody's good with this, I'm going to move on to the next slide because I got a couple things I want to do. So, all right. So, excuse me. All right, so let's just sort of summarize where we're at so far. That U does not look like a U. So summary. So if we look at gross section yielding, we got a capacity of 318.6 kips. But for net section fracture, we got a capacity of what, 255.6, was that right? There we go. So we've assessed 2 different limit states, one where we're governing yielding in the gross section and one where we're governing fracture in the net section. But if we want a simple, expression of how strong is this member, in other words, how much load can we place on this member without violating the limit states, what would the answer be? Would it be the 318 or the 255? 255. So a simple answer to, we'll say, phi PN would be 255.6 kips. In other words, that is how strong the member is. That is how much resistance the member contains. Now, if you're still a little like, well, I don't really understand what that means, I don't really understand what that value represents, I'm going to do something a little bit off to the side that maybe will help clarify what's going on. So let's do a little bit of calcs off to the side. Okay. Now I want to describe the following. Okay. Let's say the member is subjected to the following. And I'm going to say it's subjected to the following, what I'm calling service loads. Now, service loads, that's just a fancy term for indicating loads that are unfactored, okay? Okay. So let's say that the member is subjected to the following loads. And I'm just coming up with some values. So we'll say it's subjected to a dead load of 80 kips and a live load of 90 kips. And for the sake of discussion, let's assume that that 90 kips has already underwent the whole live load reduction stuff that we talked about in concrete design. So we've already reduced it and we've got a value of 90 kips. So let's just keep it basic, okay? If I give you a dead load and a live load, what do you think we ought to do with those loads? Factor them, okay? And what's the load combo that we used off our last homework and one of the ones we're going to use throughout the majority of the semester? There we go, 1.2D plus 1.6L. So let's calculate that out. So therefore, we'll call this P sub U the ultimate factored load. is 1.2 P sub D plus 1.6 P sub L, which is 1.2 times, what, 80 kips plus 1.6 times 90 kips. Now, if I calculate that out, what does that come out to be? Actually, let me write like this. $240. I have a second on that? Yeah, okay. Okay. Now, let's have a discussion about that. So, if the member is subjected to a dead load of 80 kips and a live load of 90 kips. Now, let's be clear, okay? In reality, if I took a really high-capacity bathroom scale and I measured the load that was on that section, I get a load of, what, 170 kips? But that's not the load that I'm going to use for design because remember, there's more uncertainty associated with the live load than there is with the dead load. That's why we're bumping the live load up by 1.6, whereas we're only bumping the dead load up by 1.2. So if I bump those loads up according to their relative levels of uncertainty, I get a usable load, a factored load of 240 kips. Now, that's how much force is actually being applied to the member. So I'm taking the member and I'm yanking on it, and from applying appropriate factors of safety, 240 kips is what I'm going off of. Now, let's take that 240 kips and compare it to how much load the member can withstand, which is 255.6 kips. Now, based on these numbers, is this member safe or unsafe? It's safe. It's good to go, right? Now, what if this was not 255.6? What if it was 155.6? What would be the issue there? That'd be failure is imminent, right? So if that was the case, what do we as engineers need to do? And the answer is not run. Make it bigger. By and large, that's the answer. We need to make it bigger. So that's what we mean ultimately by design. What we're going to be doing for design is we're going to be choosing a member. Instead of a W8 by 24, maybe it's a W8 by 30 or 32 or what have you. We're going to be choosing a member such that its factored resistance is bigger than its factored load. That's design in a nutshell, okay? Does that make sense? Everybody okay with that? Okay, now, we're not done though because I've got one other thing I want to assess, and what's that? Looking at the problem, what's the one thing we haven't done? Slenderness. Now, I asked you this earlier. What is the minimum radius of gyration? Ry. And what is that? 1.61 inches. What is the length of this member? 40 what? Feet. Anybody see a problem with that? So what is that in inches? Got to break out the calculator. It's Monday morning. Oh, no. What do we got? 480. All right, I got a second on that? There we go. Everybody woken up. So now let's calculate L over R. Now what are the units for L over R ultimately going to be? No units. Yeah, it's going to be unitless. So L over R is 480 inches over 1.61 inches, and that comes out to be what? So 298, we'll say 0.1. Is that good? That's good. So because that is less than 300. So if you want, usually in engineering, it's common to put something like an OK next to that because that meets the limit. If it's not OK, then you'll sometimes see an NG for no good. So it's either OK or no good. All right. Sound good?
Does RISA calculate multiple members like this and give you a kind of an idea of which one?
Yeah, it will. The question you're asking is very loaded. So let me answer it a couple different ways. Do you remember in RISA when we would specify these like basic load cases, and then at the very end we would just do, like when we did load combos, we would just say basic load case 1 and then a load factor of 1. You remember that? Well, what we would really do if we were analyzing, a full-scale building is we would have a load case with the dead loads and a load case with the live loads and then the snow loads and then the wind loads. And then RISA already has a lot of these load combos built into it, so you can just hit go and it'll do all of this factoring for you. But keep in mind, that's for a full-scale building. That's point 1. Point 2, RISA has built into it the shape database. All those shapes are in there. And it will do fundamental checks for you. But let's be clear. If you're just going to, draw a bunch of lines on RISA and input some buttons and hit this little design check button and put the blinders on, and, as Obi-Wan did, put the blast shield over and just act on instinct. If you think that will work, it won't. You got to make sure that what RISA is doing makes sense. Okay? What's that? Oh, that's right. He put the blast shield on Luke's. Yeah, that's what happened. So, coffee hadn't kicked in. I should have gotten that right, though, being a sci-fi fan and mentioning lightsabers every day. Probably, yeah. Yes. What do you mean? Well, I guess what you're saying, yeah, I guess that's true, but how would you connect that member to the structure without some connection? Now, let me say this. You could weld it.
Well, the reason I'm asking that is because most times, isn't most of your steel already fabricated? Like you have to pick what beams you want to use based off like a catalog of what beams they make.
Well, that's what that is. That's what the steel manual is. But, I mean, again, you're going to have to connect it in some way to the structure. I mean, let's say we're talking about tension members, okay? A very common place for tension members to go is either in a truss or in some bracing system for a building, right? I mean, you can't just sort of sit it there and that's it. You have to connect it to the rest of the structure. Now, you could use welds, and if you used welds, yeah, you'd have a stronger net section capacity because you wouldn't be removing material due to the presence of bolts because there's no bolts. But whether or not you use a bolted connection or a welded connection is not a simple answer because, I mean, there's fabrication involved with either aspect. So there are places where bolts make sense and there are places where welds make sense, and you kind of need to be able to assess both. Does that make sense? All right, everybody else okay with that? Everybody good? Okay. All right, any questions about this? So does this member meet slenderness limits? Yeah, but it barely meets them, right? So in other words, we got a 40-foot long W8 by 24. We wouldn't want it to be 41 feet long, would we? Then it'd start getting tough to handle, right? Right, it'd be hard to handle. All right. Everybody good? Okay, so let's be clear on what our, I guess, purpose was with this example. Our purpose was really to assess two things. Number one, we wanted to be able to determine the capacity of this member according to yielding and fracture, which we did. And ultimately, by and large, the capacity was around 255.6 kips. You would then compare that against a load to see whether or not the member is safe or not. So I came up with some random loads, and ultimately it was fine. We also determined whether or not the member meets slenderness limits, and we found it did. So, yes, sir. That's a good question. I would say ultimately the answer to that question is no, and here's why. If you technically open up the spec and you read what are the slenderness limits, there are no slenderness limits in the spec. What we're using is a suggestion, okay? So I would say we can hang our hat on using that as a suggestion. If it gets larger than that, I mean, again, we're not violating the spec. It's just becoming a little hard to handle. So I would say, yeah, if you're at 298 or 299, I mean, that's fine. I mean, I wouldn't violate it, but I'd say it's fine. One other point I'll mention is, let me take your question and extend it a little bit. So going back to those loads that we looked at earlier where we had 240 and we had what, 255.6? What if it was 240 and it was like 240.1, okay? The question becomes, well, should you use that member or should you just bump it up? No, use the member, okay? Because let's be clear. Let's talk about what goes into those numbers, okay? Remember, we take the dead load and we bump it up 20%. We take the live load and we bump it up 60%. We take the fracture capacity and we bump it down. We reduce it, to 75% of its original value. So be clear. All those factors of safety are already built in. You know what I mean? So are you going to build in all these factors of safety and then it gets real close? Well, there's already a factor of safety applied. Let's put another one in because that just makes me feel all warm and fuzzy. No, if it matches, use it. Okay, that's the whole point. Okay, does that make sense? That's the beauty of using, something like LRFD. Those factors of safety that we're using, I mean, they weren't selected arbitrarily. I mean, they come from years and years of monitoring real structures. Okay, looking at the behavior of real systems as these elements were installed. So, if it works, use it. That's what the spec is for. Okay? That make sense? Everybody else okay with that? Okay. All right. What I want to talk about is design. I want to talk about designing an element. In other words, selecting a member. If I give you a dead load and a live load, now you need to select something. Now you need to open that manual and find an element that works, okay? That's the nuts and bolts of design, no pun intended, okay? Now, all right, a couple things about the design stuff that we're going to do in this class, okay? And by and large, this is going to hold true throughout the semester, okay? When we design, we are going to design in this class by selecting the most economical section possible, okay? Now that's a loaded discussion in and of itself because, let's say I have I'll just give you an example. Let's say somebody was designing this building, and let's say somebody was designing the floor beams for this building, and there's, hundreds of floor beams, and let's say they did the math, and every single floor beam in this building, you could use a W18 by 55. But there's that one floor beam over here that, we could actually probably reduce that one to a W18 by 35. Probably just to keep the project simple, why don't we take this one and just bump it up to a W18 by 55? That way they're all the same. It's the same order, the same fabrication schedule. Ultimately, it's going to save time and money on the project. So we're taking that one and we're not using the lightest element possible. We're bumping its weight up a little bit. But in the end, in regards to the whole project, looking at the final bill at the end of the day, we're probably saving a little bit of money and a little bit of time. Does that make sense? So I want you to understand that what we might do in here, like when I grade your homeworks and your exams, I'm going to be just saying, okay, for this problem, are they selecting the lightest element possible? But this problem in the context of a whole project, that might not be the most economical. Does that make sense? Everybody okay with that? All right. Now, quick question. If I have a W10 by 55 or a W10 by 49, which is lighter, the 55 or the 49? 49. And how do we know that? The 49 represents pounds per foot. Okay? So for the problems that we do in this class, we're always going to go with the lightest shape possible. Because lightest shape is ultimately, if all we're looking at is that particular problem, in the context of that problem, lightest shape is going to mean most economical because lightest shape is less pounds per steel, and if steel is priced per pound, less money, less hit on your wallet for that particular element. Make sense? Okay, all right. All right. So for us, lightest shape's always going to work. Okay. Now, what we're going to do is we're going to design ultimately based off the following three limits: yielding in the gross section, fracture in the net section, and slenderness. Okay? Now, the yielding in the gross section and the slenderness, they're pretty easy. Okay? They're pretty easy to design off of because you can just solve accordingly. Okay? Fracture, that takes a little bit of discussion. Okay? But let's handle the simple ones first. Okay? Now, let's talk about yielding in the gross section. Okay, so let's be clear on what we're trying to do here. We're now in a world where we don't have a clue what the element looks like. It's not like the last example that we did where we're given a member and we have, its member size and all this. We don't know because we're in design mode. Okay, our job is to select that member. Okay, but let's be clear. If we're talking about yielding in the gross section, what's our fundamental design philosophy? Our factored resistance has to be greater than or equal to our factored loads, right? Now, what is our factored resistance according to gross section yielding? Well, phi is 0.9, right? And Pn, our nominal capacity, is the yield stress times Ag. Make sense? Now, we're in design mode, okay? What we're solving for is the area. We need to pick a member that meets this area requirement, okay? So I'm going to solve for gross area. So solving, dividing out everything on the left, I get the load. Remember this load, that's your 1.2 dead plus 1.6 live, what have you, divided by 0.9 Fy. So I propose that when we are selecting members, we need to select a member such that its gross area is at least Pu over 0.9 Fy. Everybody okay with that? Okay. Now I'm calling that Ag min 1 because I'm ultimately going to solve for an Ag min 2 for fracture. So if you're wondering where the 1 and 2 come from. Okay, so that is yielding. Now let's look at slenderness. Okay, slenderness is simple. Okay, L over R has to be less than or equal to 300. So just solve for R. Okay, if we're talking about a truss or a bracing system in a building, we know we're selecting a member, let's say if it's in a truss or some bracing system, we know we're selecting a member, let's say, for right here in that given bracing system. So we know how long it's going to be, but we don't know the properties of the cross-section. We don't know if it's a W10 by 35 or a W10 by 49, so we don't know R. That's what we can solve for. So its minimum radius of gyration has to be equal to L over 300. So if I'm talking about a W section, I'd go through the W sections, and I'd find a member that has an RY of at least L over 300, because remember for W shapes, RY is always the smallest one. Sound good? Bless you. Everybody good so far? Now, here's the complicated one. Okay, let's actually take this out. Let's see if we tried to solve for a nice, pretty expression for a net section fracture. It would get a little complicated. Okay, here's why. All right, we start off with the very beginning. Phi Pn has to be greater than or equal to Pu. Our factored resistance has to be greater than or equal to our factored loads. Okay, now what is our factored resistance according to net section fracture? Well, Phi is 0.75, right? And our nominal capacity is our tensile stress times AE, which AE, that gets a little complicated because you have to take the net area and adjust it by the shear lag factor, right? Now, how do you calculate net area? Well, you take the gross area and you subtract your bolt holes and you add your stagger factors, right? Now think, we don't have a clue what the member looks like, you know what I mean? So how do we do that? That's tough, you know what I mean? That's not easy. First off, we don't know what, there might be a lot of stuff going on in this little bracket, but what about U? U is highly dependent on the member we're looking at, the connection eccentricity. We have no clue what U is, And at the very least, think about net area. The most simple explanation of net area is that it is the gross area minus the area lost due to bolt holes. So at the very least, we're going to have a thickness, you know what I mean? Well, we don't know what that thickness is because we haven't selected the member yet, right? So here's what I'm going to do, all right? What I'm going to do is I'm going to make a very basic assumption right off the bat. I'm going to assume that the effective net area is about 75% of the gross area. So this is taking the gross area, removing the bolt holes, getting to net area, and then adjusting by U to get effective net area. Now, let's be clear. This is an assumption, okay? Because it is an assumption, when we select a member, it will be a trial member because we have to go and check that member and validate those assumptions that we made, okay? That's where design becomes an iterative process. We might select a member, and we might go through, do all the math, that member that we selected, it's not good because we selected it based off some assumptions. So we might then have to select another member and do it again. So that's where design becomes a little bit of an iterative process. But this design assumption that we're using is usually a pretty good one. It should, in most cases, cut out a lot of the iteration. So let's carry this assumption out a little bit and let's see what happens. So phi PM has to be greater than or equal to PU. So phi is 0.75, PN is FUAE. Sound good? Now, for AE, I'm going to substitute 0.75 gross area, and that'll account for an assumption that'll account for my shear lag factors and my bolt holes. So if you notice, I've got two 0.75s in here. One of them is the phi factor, that's this one right here, and the other one is that assumption to account for shear lag and our bolts. Sound good? So I propose that another gross area requirement that we can compute is our load divided by FU times 0.75 squared, okay? Now again, there's a lot of assumptions going into this. That's why when you pick a member, it's a trial shape and you have to go and check it. So far, so good? Any questions? All right, so here's a little slide that maybe you can summarize or put a little star next to. This might make your life a little easier for referring to your notes. We can select members based on the following assumptions: that our minimum gross area has to be our load divided by the minimum of these two values. Because the smaller denominator is going to result in a larger gross area. I mean, think, if you calculate a gross area requirement for yielding and fracture, and yielding tells you you need about 7 square inches, and fracture tells you you need about 9, do you want to be selecting members that have at least 7 square inches or 9 square inches? Think about that. Let me ask that question again. All right, I want you all to think about this. I know it's Monday morning and the coffee hasn't kicked in, but bear with me. So we got two limit states. We got yielding, we got fracture. Now, yielding tells us when we pick a member, it's got to have at least 7 square inches. But when we do fracture, fracture tells us we got to have at least 9 square inches. Now, you're the designer and you're picking that member. Are you going to pick a member that has at least 7 or at least 9? At least 9. There we go. All right, makes sense? Because if you pick a member and its area is, let's say, 9.5 square inches, it's going to meet the requirements, assuming all your assumptions are valid, of yielding and fracture, right? But if you pick a member and it's only got 8 square inches, you're going to violate one of those limits right off the bat, right? Make sense? And that's what's going on here. That's why you think a smaller denominator is going to result in a bigger computation. Make sense? All right. So we have a minimum gross area requirement and we have a minimum radius of gyration. So based on these, we can compute what's our required member that we need to select. So that's a starred slide if I've ever seen one. Okay. Keep in mind, these are assumptions, so we're going to have to go back and verify our design. Now, how do we know if our design is the most economical? Well, an easy way, or it might be the long way, but it's an easy way. The long way would be to do the following. Let's say I pick a member, I do all the math, and I check it, and I find it's good. An easy way to check whether or not that's the most economical design is to pick the next one down and do the math again, okay? Because if I've got a member and it works, and I pick the next one down and it doesn't work, then the one I had before, that's the most economical, right? Because the one below it fails. So an easy way, but a long way, is to just do the math again. But a nice rule of thumb that you can use is to calculate what's called the efficiency. In the world of bridge engineering, we call that a performance ratio. It's all the same thing. The performance ratio, or efficiency, is to just take the loads and divide it by the resistance. And if you're getting a value that's around 0.9 or higher, that's a good check that your member's the most economical selection. So in other words, if you're on a test and you do all your math right, and you calculate efficiency, and efficiency comes out to be like 0.95, but just based on random probability, the next member does in fact actually work, I'd still give you full credit if this value is 0.9 or higher, okay? So don't worry, all right? Sound good? Does that make sense? One other point I'll mention, Usually on tests, I design the problem so that doesn't happen, okay? I'm not a fan of you all just sitting there iterating over and over and over and over again on a test. That's not the point, okay? Sound good? All right, so we finally get to at least start a design problem. I'm sort of excited about that. We definitely won't finish it, but let's go into the problem a little bit. Let's explain what's going on. Okay, so we're going to do a design example. So I'm going to design a member that's 30 foot long. So there are some values that I am giving you at the beginning, which A, is realistic of what is going on in the real world. I mean, if you've got to design a system for a building, well, the architect's going to come in and say, here's about where the frame needs to go. So you're going to have a general understanding of the geometry. And you also are going to have at least a reasonable understanding of the limits on your members. I mean, right here behind Mr. Schaffer, there's a column right here, okay? All right? Now, the architect only gave the engineer so much space to put that column in here, right? I mean, the column can't go all the way out here. You know, we might be able to get a lighter shape, but nobody's sitting here. They might not have a good time, right? Make sense? So it's pretty reasonable to have certain limits on your design. For instance, we're selecting for this member, we're selecting a W12, okay? So what that means is that for this member, we're limiting its depth to about 12 inches, okay? And that could be based off of architectural considerations, architectural restrictions, what have you. And that's very realistic. Okay. Now, the member's 30 foot long, okay? It is being subjected to the following loads. We've got a dead load of 130 kips and a live load of 110 kips. That 110 kips is already reduced, so we don't have to worry about live load reduction. Now, we're going to select a W12 section. Now, if you go back to this table right here, remember this, where we were looking up FYs and FUs, table 2-4? You'll notice that for W shapes, by and large, the most, or the preferred material specification for the W shapes is an A992, and I want everybody to look at this right here. So, table 2-4 on page 2-48. If you haven't already tabbed it, that was one of the ones that we indicated you ought to tab. Everybody see that? Now, what is the preferred material specification for a W shape? And you'll note that by the black cell in the table, because you've got gray ones, white ones, and black ones. So what's the preferred material spec for a W shape? A992. What that means is that when I go to a service center or a mill or something like that, and I say, hey, I need to buy a W10 by 49, by and large, I'm going to get it in A992 steel. That's the preferred material spec for that shape. Now, if I want, I could get it in, A913, A572, A529, and what have you, but the preferred material spec is A992. So really, unless otherwise noted, this is sort of what we're going to go off of, because in reality, when you go and buy a shape, that's what you're buying, okay? You'll note that there's a lot of design aids that we're going to use throughout the semester, and if they're referring to W shapes, those design aids are going to be W with an FY of 50 and an FU of 65, because that's the preferred material spec anyways. Make sense? Okay. So you'll notice that for this design problem, there are some limits that have been put on you. You know, it must be a W shape. It must be a W12. So W12 by something. I've even given you some reasonable parameters for the connection so that you can design that. Later on, we will learn how to design the connection itself. You know, how many bolts and how to space them apart, and et cetera, et cetera. But I'm doing that because right now I want us to all sort of arrive at the same answer. In other words, if I just said, hey, design a member that's got 130 kips of dead load and 110 kips of live load. There's 22 people in the class. I could get 22 different answers and they'd all be right. You know what I mean? So I'm trying to reduce the process so that we'll all arrive at the same answer. Okay? But in actuality, man, let's be clear. There's a bigger picture going on. There's the scale of the project, material availability, and all that. So there's a real world aspect to what's going on as well. You know, maybe the member that we pick, maybe it's not available. And if you pick a a little bit of a bigger member right now, you'll get it faster and ultimately get the project done faster. Maybe that's the most economical option. Sound good? Any questions? All right. Let's see. So, what time is it? We'll do a couple, quick calculations to get this example moving, and then we will probably call it for today. But I do want to at least get us started. Okay. So, help me out with something. So we've got some data here. What do you think is a good first step in our design? Right? If you were given this design, you didn't know what to do, what's the first thing that you could do right now given this data? Factor the loads. There we go. Factor the loads. So let's do that. Simple, right? All right. It's example 4 or 5. 5. Factored loads. Okay. So we're factoring loads based off the following. We have a dead load and a live load, and what are those? There we go. So tell me what to do. Have you tell me what to do. Oh, okay. All right. So PU, 1.2 times the dead plus 1.6 times the live. So what does that come out to be? 332. Now, we have been using 1.2 dead plus 1.6 live because, by and large, it is one of the most common load combinations that we will use. Are there any other ones? There's 8 more. Where are they? They're in the manual. Now let's find them. Let's find them. Say it again. Page 2-11, and also 2-10, right? Remember I told you this a slide or a section in the manual that you might want to place a tab in, right? Everybody remember that? Everybody, I want to make sure everybody finds this. Everybody got it? There we go. Are there any other load combos that maybe we ought to look at? Now let's be clear. All we have is a dead load and a live load. So for instance, we probably don't need to look at load combo 3 because if all you've got is a dead load and a live load, that would be 1.2 dead plus 0.5 times the live. That's certainly not going to be less than this one because this is 1.2 dead plus 1.6 live. Were you able to find it? All right. What other one y'all think we ought to look at? What about 1.4 times the dead? Maybe we ought to look at that one. Let's go ahead and compute that. So what is 1.4 times the dead? So what I might do is I might say PU sub 2, and this is PU 1, 1.4, 130 kips. 182. I got a second on that? Okay, all right. So are there any others that we ought to look at? You think that's good? It's probably good, right? Again, that's assuming all we've got are dead load and live load. If we had snow, if we had wind, we'd have to go through and do them all, right? So this is one of those things I just want to make sure that everybody's all right with. And I'll go ahead and list my reference, and I'll say page 2-10. So for design purposes, what should we be using? 332. All right. Everybody okay with that? All right. Let's see what time it is. All right, I think I'm going to call it today. What we're going to do is we're going to pick it up next time, and we're going to actually design this member. So yeah, we'll call it now. Just one other thing real quick. Again, please try and make sure you're here on time on Wednesday. If you did not get a homework 2, I have that here. And all right, that's all I got. The sign-in sheet should have been working its way around, so if you didn't sign that, it's probably somewhere in the back. That's all I got. All right. We will see you. Hold on, let me stop.